The method of variation of parameters is useful in solving a system of differential equations that is linear but possibly non-homogeneous. So what I'd like to focus on in this video is just to unpack the method a little bit, make sense of what this method does exactly, and to give some of the justification for it. So first of all, let's suppose that we have a system that looks like this. Now, what are we trying to say here? Well, we're suggesting that dy dt, that this is a vector of two rates of change, namely dx dt and dy dt. So this method is only going to work for a system of two differential equations. And here's the thing, our right-hand side, instead of just being of the form a times y, this matrix P can contain any functions of t. So we can kind of label those in a number of different ways, but one such way is to write the entries of the P matrix as P maybe 1 sub 1 of t, and P1 2 of t, P2 1 of t, and P2 2 of t. Now, what we're doing here is we're having that matrix multiply the y vector, and let's remember the y vector just has our two functions x and y in it. The dy dt vector contains the derivatives of x and y. And then we're going to have this plus g of t. That's going to be a vector of functions. That's actually what makes this entire thing non-homogeneous. So maybe we'll have something like g1 of t and g2 of t. So as far as what are the differential equations going to look like, well, dx dt will be p11t times x, okay? So it'll be x times the first column plus y times the second column, and then we'll have plus p12 of t times y. Okay, so this multiplies this column, and x multiplies this column. So in the bottom row, for dy dt, we'll have p21 of t times x plus p22 of t times y. And then we'll have plus g1 of t added to the top, and plus g2 of t added to the bottom. Okay, so dx dt corresponds to this top row, and dy dt corresponds to this bottom row. So how this relates back to a first order linear system of differential equations that's homogeneous with constant coefficients is previously we've called this kind of A, and we've called this B. And A and B have up until now just been constants. Though what we're suggesting with the P11 and P12 is that they could actually be any functions involving t. All right, so that means that this down here is what we would have considered our C, and this would have been, P22 would have been kind of our D. Now, up until now, we haven't had any non-homogeneous terms. This is what makes the entire system non-homogeneous, is that we have some standalone functions of t. Perhaps those are just constants, but they're other things that aren't attached to the coefficients x and y. All right, and we're saying here that if you can write the system of differential equations in this shape, in this form, and also they are continuous on an open interval. Now, we're not going to get too much into that, and it's not much of a worry as long as you don't have problems with your differential equations having possible divisions by 0 or square roots of negative numbers. Then we don't have to worry too much about the open interval condition. Now, here is the stipulation. We do have to have two solutions, y1 and y2, and we call them a fundamental set of solutions of the homogeneous equation. So this right here, notice, looks a lot like a lot like this one here, except this one has the plus g of t as well, making it non-homogeneous. So we have to be able to, first of all, find solutions, y1 and y2, to this system of differential equations. And then, as long as we can do that, then we can solve the non-homogeneous piece that has that plus g of t attached to it. And here's how you find a particular solution to this non-homogeneous equation. Because remember, when we solve a system and we find usually something like k1, y1, actually I should have capitalized that, k1, y1 plus k2, y2, and this would be our solution to a homogeneous system, but then we also have this particular solution, which I'll just call y sub p. That will be a particular solution to the non-homogeneous equation. That's, of course, going to be a lot harder to find when you have two potentially different functions attached to dx dt and dy dt. But here's how you find it. The particular solution, in other words, this last term here, after you already know what y1 and y2 are, we can find this as follows. Y sub p will equal this capital X matrix times the integral of x inverse of t, so that's going to relate to the X matrix, times g of t with respect to t. Well, what is all this stuff? Well, capital X is the matrix with y1 and y2 as its columns. In other words, this column right here, this entire column is what we're referring to as y1. That's the first solution to the homogeneous system. This is the second solution to the homogeneous system. And then we just stack those two solutions as columns inside of this matrix that we're calling X. So sometimes you'll see it written like this. You'll see X equals, and then here we'll just have y1, and over here we'll just have y2. And sometimes I'll even draw these little lines just to indicate that, hey, that's a whole column of functions, column of two functions. And, well, how do you get this X inverse thing? Well, X inverse is actually found by doing a couple of things. Notice that X has x1, x2, y1, y2, but in this matrix, notice that the diagonals got switched. So x1 moved to the bottom right, y2 moved to the top left. And then with these two functions, x2, we just negate that, we negate y1, and we multiply it by this quantity called 1 over w of x. Well, what is w? Well, w is what we call the Wronskian matrix of x of t, or excuse me, it's not a matrix, it's a value. This is just a single value, and you get it, or a single, value or expression, meaning it could involve variables, which a lot of times it will, but it's the product of, if you look inside of the X matrix, x1, x2, y1, y2, this term here, this very first term, x1, y2, well, that's the product of these two values from top left to bottom right of the original X matrix, minus y1, x2, so what are we subtracting here? Well, we're subtracting away the product of the diagonals here. If you've taken any linear algebra, which I'm not assuming in this video, but if you've taken any linear algebra, you might just recognize the Wronskian as the determinant of this matrix. Now, I'm not going to get into the theory of how we find the inverse of a matrix, but what I will say is that if you have a 2 by 2 matrix that just contains 4 components like this is 2 rows by 2 columns, and you want to find its inverse, the way you would normally find that if these were numerical values would be 1 over A times D minus B times C multiplied by dA, so switch the two components and then just negate the B and negate the C. So this is how you find the inverse of a 2x2 matrix in linear algebra. If you've taken linear algebra before, I want to hopefully make that something that you recognize. The only difference here is that in this inverse it involves functions. So we're not going to get into the details of how the inverse is computed, just that in linear algebra matrices have these things called inverses. So what do we have to do with all of this? Well, what we have to do is we have to, first of all, solve the homogeneous system. Okay, so solve this homogeneous. Be able to solve it using previous techniques, and then to solve the non-homogeneous system with this extra g of t vector here, we find this particular solution. Right? We take k1, y1 plus k2, y2, just as we've done in the past, to get our general solution of the homogeneous. But now we know that to solve a non-homogeneous, it's the sum of the homogeneous solution, which is this right here. This is what we would often call y sub h, plus one particular solution to the non-homogeneous system. And that's the really hard part to find, because we're dealing with a system of differential equations. But the way you find y sub p is to compute this quantity here. Okay, so that's what we would need to do. And I'm going to stop this video here because the goal here is just to kind of outline what this theorem is really saying and how we gathered the parts necessary to build the solution. There are going to be two major challenges here as far as the method itself is concerned. One is if P of t, that matrix, is not constant, we may not be able to actually get y1 and y2, right? Because this assumes that you can actually solve the homogeneous system in the first place, and we know how to solve a system of differential equations if the p11, p12, p21, p22, if those are constant, then we can find eigenvalues and eigenvectors, and that's no problem. But we don't know how to solve that system if those are functions. And the reality is that can get rather complex. So we're only going to focus our attention to where that P matrix consists of constants. Because in theory, this is a great theorem, but in practice, it's not very practical because, again, you need to be able to find this solution before you can even construct that X matrix. So that's the one first challenge. And then the second challenge, that even if we do get past that point, let's say we're capable of doing that, but now we have to compute this integral, right? This integral right here, it may not be able to be done. It may not have a closed form depending on how ugly, if you will, the functions inside of g actually are. So let's say you have like sine times cotangent as g1, and then you have something like t squared times e to the t times cosine t. That integral may not necessarily always be possible. So the other challenge is that the integral of x times x inverse, now I'll omit the of t notation just to keep it simpler, that integral may not exist. Okay, and that's just always a challenge in differential equations. But if we can get past those two things, then we can solve by using this variation of parameters method. In the next video, I'd like to take a look at where this stuff comes from, just so you have a good sense of what it is that we're actually doing and that this is not just an invented method.